voltage regulation of synchronous generator. Okay, so what is voltage regulation? It is a very important performance parameter, right? So you can write down, it is the measure of ability of a generator to keep a constant terminal voltage as its load varies, right? So we know that the terminal voltage is equal to the generated voltage, the actual generated voltage, minus the voltage drop across the parameters, machine parameters, armature resistance and the synchronous reactance. So this Vt is going to depend on Ia. As load increases, it means that the current is increasing, so the voltage is reducing. Now ideally what we want is, we want this parameter to be 0, okay, so that the voltage is remaining constant for any load. But since it is not actually going to happen like that, we want this to be as negligible as possible. When this is negligible, what will happen? Even much higher variation in the load current is not going to affect the voltage drop too much. But if these parameters are also high, then the variation will be higher, okay. So this is the information that you are going to get from voltage regulation. So how do we define voltage regulation? Percentage voltage regulation we take as the no load voltage minus the full load voltage as a percentage of the full load voltage into 100 will give you the percentage, okay. So this is how we mathematically define the voltage regulation. In order to find this voltage regulation, we make use of three methods. So the very first one is the synchronous impedance or EMF method. So first we will see what this method is. Here we make use of the open circuit and the short circuit characteristics, right? So we found out that from both of these at a particular field current, we can find out the synchronous impedance. What is it? It is equal to the generated voltage at open circuit, that is no load condition, divided by ISC, that is the current, armature current at short circuit condition. And then we can find out the armature resistance from the DC test. So we will get the synchronous reactance as well. This is equal to ZS square minus RA whole square. So once we know these parameters, then we can find out the generated voltage at any load and any power factor can be found out. So what was the equation? Eg is equal to V cos phi plus Ia Ra whole square plus V sin phi plus Ia xs whole square. This is for what? Lagging power factor. If we want for leading, then here negative sign will come, okay. So this is how you will find out the generated voltage at any power factor at any load, and once you can find this, then you can get the voltage regulation as Eg minus the terminal voltage at full load divided by the full load voltage. So we will make use of a problem to understand this method. A three-phase star connected alternator is rated at 1500 kVA, 12,000 volt. The armature effective resistance and synchronous reactance are 2 ohms and 35 ohms respectively per phase. Calculate percentage regulation for a load of 1200 kilowatts at power factor of 0.8 lagging. So we will first write down what is all the information that is available to us. So the rated voltage and kVA is given. What is the rated kVA? This is given as 1500. And what about rated voltage? This is 12 kilovolt. Then the armature effective reactance, this is given as 2 ohms, and the synchronous reactance is 35 ohm, this is These are all per phase values. Okay, so that means you can draw the equivalent circuit diagram, per phase equivalent circuit diagram. This is RA XS. Now remember one thing here, when the rated voltage and kVA is given for the alternator, it is usually given as the 3-phase kVA and the line voltage. So only these two are the per phase values. So you're going to write here, this is V phase. What will it be? 1200 divided by root 3, because it is given as star connected alternator. Okay. Now we have to find out the percentage regulation at a load in kilowatt is given as 1200. What is the power factor? This is given as 0.8 lagging. So we know the power factor, we know the phase voltage, terminal voltage, RA and XS. Now if we want to find out the generated voltage, then we need another value, which is the load current. So that we can get from this value here. 1200 kilowatt is the given load. So this is the 3-phase load once again. So you're going to write load in kilowatt. 3-phase load in kilowatt is given as 1200. So this means that root 3 VL IL cos phi is equal to 1200 into 10 cube. So this will give you IL is equal to 1200 into 10 cube divided by root 3 into 12,000 into power factor, which is 0.8. So you're going to get 72.16 amperes here. Okay. So now you can find out EG. This is equal to root over V cos phi plus IL RA whole square. So this is star connected. So whatever will be the line current will be the phase current as well. Okay. But here this is going to be the phase current plus V phase sin phi plus IL XS whole square. Okay. So you're going to substitute all of the values. 12,000 divided by root 3 into 0.8 plus 72.16 into 2 whole square. The line current is same as the phase current, plus 12,000 divided by root 3 into 0.6 plus 72.16 into 35 whole square. So these are all of the values which are already known or they are given. Okay. So the final answer you're going to get is 8774.5 volt. Okay. So now you can find out the voltage regulation. If you are using the phase voltage, then the terminal voltage also you will use the phase voltage. Otherwise you will use the line voltage in both the cases. Okay. So percentage voltage regulation is equal to 8774.5 minus 12,000 divided by root 3 divided by 12,000 by root 3. Okay. Into 100. So you're going to get 26.6%. Now the next method that we have is the ampere turn or MMF method. Now the EMF method that we first discussed, that was pretty straightforward, right? Now what happens is the armature reaction, the leakage reactance and all these are converted into EMF form. That means in terms of a voltage in the EMF method. In the MMF method, what you're going to do is you're going to make use of MMF in order to represent these armature leakage and armature reaction. Okay. But we don't need to go into all of those details. What we want is how to find out the voltage regulation using this MMF method. Only the procedure we need. Okay. So the first step is to plot the open circuit and short circuit characteristics. So let us say here we have the field current and on this axis we can draw the voltage for the open circuit characteristic, and for the short circuit characteristic you can draw the current here. Okay, so this is the open circuit characteristic and the short circuit characteristic you can draw like this. Okay, so this is the short circuit characteristic. Now we will need one reading from both these curves. So what are these two readings? The first reading from the open circuit characteristic. We will find out the voltage which is equal to the rated voltage, rated full load voltage plus IRA cos phi. So this is the cos phi is the particular power factor at which we need the voltage regulation. Power factor at which voltage regulation is to be calculated. Now let us take this voltage to be V1. So for this voltage V1, what is the corresponding field current for the open circuit characteristic? So let us say this is IF dash. So from the graph you are going to get IF dash. From open circuit characteristic, find the field current for getting voltage V1. Okay. Next, from the short circuit characteristic, we want the field current which will give the rated current. So from SCC, find IF double dash to give rated full load current. Rated usually means full load only. So say this is the full load current somewhere here. So you are going to get IF dash here. So once we get this IF dash and IF double dash from the open circuit and short circuit characteristics, then the next, what will be the next step? You have to construct IF as the reference phasor. Now IF dash as the reference phasor. Now IF double dash you will construct in such a way that this angle here is the corresponding power factor angle. Okay. Now when you add these two phasors, then you are going to get the field current at the required power factor at full load. This IF dash and IF double dash, they together represent the various phenomena that are happening in the synchronous machine. Okay. What are the various things? The armature drop, the effect due to the leakage reactance and armature reaction. All of this are now, we have converted it in terms of the field current instead of the voltage. So field current is what? It is nothing but the MMF, because MMF is nothing but the number of turns into the current. N into I gives MMF. Okay. So that is why we have converted all of the effects of the synchronous machine in terms of the field current, which is why it is called MMF method. Now we need to get back the voltage, because finally we want the voltage regulation. Okay. So now what we do? This field current that we obtained, this represents the field current that is required to get the voltage at full load and the required power factor. So we have included the power factor here. Okay. So in the graph, once again, you will find out what is the voltage, the open circuit voltage for this particular field current. Okay. So once we find out the open circuit voltage for this particular field current, then we can find the voltage regulation. Let us take this voltage to be EG. So we can write the fifth step, find the voltage corresponding to the field current IF on the open circuit curve. Let us say this is EG. Okay. So now finally you can find out the percentage voltage regulation as EG minus the full load or the rated voltage divided by the full load voltage into 100 will give you the voltage regulation in percentage. So the final method that we have to find out the voltage regulation is zero power factor method, or this is also abbreviated as ZPF, and it is also called as the Portier triangle method. Okay. So for this we will be needing two characteristics. First one is the open circuit characteristics, that is the OCC, and second is the zero power factor characteristics. Now we know what is OCC. So what is this zero power factor characteristic? It is the plot of the terminal voltage versus the field current for a purely reactive load. So if you plot both the characteristics on the same graph, here you will have the terminal voltage, the field current. Now the OCC is going to look something like this. Now the ZPF is going to be exactly similar to OCC, just that it is slightly shifted to the right side. So this is the ZPF. Now once both these plots are available, then you will have to construct the Portier triangle. After OCC and ZPF are plotted, construct Portier triangle. So this you can in fact write as the step 1. Now the question is how to construct this Portier triangle. How to construct. So what you will do is, at the rated armature current, what is the field current? You will mark that point on the ZPF. IF for rated current. Now through this point we will draw a parallel line whose length is equal to this length. So you can mark the points here O, A, and if this is B. Okay, you will draw a parallel line so that this length BC is equal to OA. Now next what you will do is you will construct a line. This is the air gap line, right? So now you will construct a line parallel to this air gap line passing through C. Okay, so that is going to look something like this. Okay, so now you have this point here, you can mark it as D. BCD is nothing but the Portier triangle. So you can write down BC is equal to OA, CD is parallel to air gap line. So you are going to get the Portier triangle BCD. Now once you get the Portier triangle, then what are you going to do? Step 2, you are going to mark some data. So what is the data? You will draw a perpendicular from D onto BC. So let us say this is point E. Now this DE will give you the leakage reactance drop, voltage drop. Okay, and EB will give you the armature reaction in terms of MMF. So what is the reason for this? We will discuss later. Okay, for now you just need to know that DE will give you the leakage reactance voltage drop and EB is going to give you the reaction, armature reaction MMF. Now once you get this data, what is the next step? Step 3 is to find out leakage inductance or the leakage reactance. This is equal to DE, which is nothing but the voltage, divided by full load current. You can write per phase current. This is important here. This is also per phase voltage. If you are taking line voltage, then you will write √3 extra in the denominator. Okay. So now you will find the leakage inductance. Next you can find out the excitation voltage only taking the leakage drop into consideration. Forget about the armature reaction. Okay. So what will that be? ER will simply be the terminal voltage plus J times IAXL. So this will give you the magnitude as well as the phase of this particular voltage. Okay. Consider this as the intermediate voltage. We still have not gotten the open circuit voltage. So how to get the open circuit voltage? We also have to take the armature reaction into consideration. So how to do that? For ER, find the field current from OCC. So that means in order to get the open circuit voltage of ER, what is the required field current? Okay, so that's what we are finding out. Once we find this field current, then what we will do? Step 6, find equivalent field current, which will be the phasor addition of, you can take this as IFR. So IFR plus IFAR. So what is IFAR? That is the field current required for the armature reaction. So you can write down, which takes care of the armature reaction, and this takes care of the terminal voltage plus the leakage reactance drop. Now IFR you have found out from step 5. What is IFAR? This is what we found out, the second value that we found out from the Portier triangle. So found from Portier triangle. Now the magnitude you can find from the Portier triangle. What about the phase? The phase of this armature reaction field current is going to be the same as the armature current phase. Okay, so that means if you have a load of cos phi, let us say, okay, that means if Vt is like this, then the armature current Ia will be lagging by phi. Okay, so if you take Vt as phase 0, then IFAR phase will be same as the phase of Ia, which means minus phi. Okay, so we will construct a proper phasor diagram so that you will understand better. Say the terminal voltage Vt we will take like this. Okay, so for a load having a power factor phi, you will have Ia like this. Okay, now what will be the leakage reactance drop? That will be leading the current by 90 degrees. Okay, so Vt plus the drop across leakage reactance will give you ER. So you are going to draw a phasor which is perpendicular to Ia. Okay, so this is JIAXL. Okay, so now if you add both of these, you are going to get what? ER. Okay, now the field corresponding to this ER, that means IFR, that will be 90 degrees leading, because flux leads the voltage by 90 degrees. So you are going to draw IFR like this. Okay, next you can draw IFAR such that this and this are parallel. Okay, so now when you add both of them, you are going to get the required field current. Let us write this as equivalent. Okay, so IF equivalent. Okay, so finally from this particular, once you find out this equivalent field current, you will get the corresponding open circuit voltage from OCC. Okay, so you are going to write step 7, find open circuit voltage from OCC at the equivalent field current. Okay, so this is the final open circuit voltage which is taking care of the armature reaction also and the leakage drop as well. Okay, so once you find it out, then rest of it is as it is. The voltage regulation is going to be the open circuit voltage. So let us take this as EF. So EF minus Vt divided by Vt into 100 will give you the percentage voltage regulation. So now one point is left out from the Portier triangle. How do we get this data that this base is the leakage drop and this part is the armature reaction MMF? So we will try to understand that. We will start from the equivalent circuit of the synchronous machine. So the equivalent circuit consists of a voltage source in series with resistance and inductance. Okay, So the voltage that is available here, this is the terminal voltage. Okay, and this is the armature resistance, and we have the synchronous impedance, and this is the generated voltage. Okay, so now in this inductance we are considering the leakage drop as well as the armature reaction. Okay, but we will make a slight modification and some assumptions as well. So the very first assumption is, assume RA to be negligible. So when we are doing the Portier triangle method, we are having these assumptions. Okay, because anyways resistance is very small, so it is a valid assumption. Okay, and the second modification that you're going to do is the armature reaction effect that we are considering as part of this inductance, we will separate it and we will only take the leakage drop here. So what will happen in that case? This EG will be different now. Okay, so the second change is modify XS and EG. So you are going to be left out with this, we will take as ER, and the armature resistance we are neglecting. This will be the leakage inductance, and here anyways we will have the terminal voltage. Okay, so the armature current is going to flow like this. Here also you can represent the armature current. Okay, so now at ZPF, that means zero power factor, what will happen? If the terminal voltage is like this, then the current is going to be lagging by 90 degrees. Okay, so even if you did take the resistance, since the resistance is very small, this angle will be close to 90 but less than 90. Okay, so this is how VT and IA will be related at ZPF. Now what will be ER? It is the addition of VT and the drop across the reactance. Okay, so you can have here this, you can write VT here. The drop across the leakage reactance will now be leading this current by 90 degrees. Okay, because it is a pure reactance. So you are going to have IAXL like this, only this part is IAXL. Okay, so from here you are going to get ER. Normally though we will represent in terms of phasor, VT bar plus IAJ IAXL, right? But since they are in phase, we can simply write, we can let go the phasors. So it is going to become ER is equal to VT plus IAXL. You can simply add numerical values or the magnitudes because they are in phase. So this entire phasor here, this is going to be ER. You can write ER here. Okay. Next, what will be the MMFs? The field current. Now the field current responsible for this particular voltage ER, that is going to be 90 degrees leading it. So it is going to be like this. So you can write IFR here. Okay. Next, what is left out? The armature reaction. We have removed from the inductive part and we have kept it on this side of the circuit. Okay. So now IFAR which will be the field current responsible for armature reaction. What will be its phasor? It will be in phase with the armature current, right? Because armature reaction is because of the armature current. So it is simply going to be in phase with IA. Okay. So you are going to have IAR something like this. Now this also you can see that IFR is in this direction, IAR is in this direction. So there is a subtraction taking place. So if you add both these phasors, we will get the equivalent field current. Okay. So that is going to be lesser than this IFR. So you are going to have IF equivalent here. So now this is the field current that is responsible for this terminal voltage, the final terminal voltage. This magnitude will be the magnitude of the field current required for armature reaction. So here we have the second equation. This is the first equation, and the second relation that you have is IF equivalent is equal to IFR minus IFAR. Actually, in phasor form, if you write, IF equivalent is equal to the phasor addition of IFR and IFAR. But since this IFAR is in exact 180 degrees opposition to IFR, we will write minus IFAR. Okay. So this is also the simple subtraction of numerical values. So this is the second equation. Now you go to the open circuit and the ZPF characteristics. This is the open circuit characteristic, and the ZPF, it is going to look similar, right? So this is the ZPF. This axis is the voltage axis, the terminal voltage axis, and this is the field axis. Now if you consider a point which gives the rated terminal voltage, right? You can write here rated. Then for this particular, in order to get this particular voltage, what is the field current? It is IF equivalent. Now how do you get the corresponding open circuit voltage? For this particular terminal voltage, what will be the open circuit voltage? So that is what we are making use of the Portier triangle, right? So this is how the Portier triangle is going to be. So this line here, this is parallel to the air gap line. So the reason is, you can draw the Portier triangle at any point on the ZPF. So if you take this starting point, then the triangle is going to be like this. Okay. Now this triangle and this triangle is similar. Now this slope here, this side of the triangle is nothing but the air gap line. We can approximate this part of the curve as a straight line, which is the air gap line. The initial slope is the air gap line. So that is why here this side also we are drawing the line parallel to air gap line. So wherever it is intersecting the open circuit, that will be now the required open circuit voltage in order to get this terminal voltage. Okay. So this value is ER. But from the first equation, what do we have? ER is equal to VT plus IAXL, which is the drop across the leakage inductance. So now ER is this, on this axis if you see, this entire part is ER, this part is the terminal voltage. So the remaining part that we have here is the drop across the leakage reactance. So this part is nothing but the perpendicular drop here. So this is equal to IAXL. Okay. Now similarly, using the second relation, we can get this point as well. What is IF equivalent? This is equal to IFR minus IFAR. Now we know that in order to get ER, what is the corresponding field current? Here we have drawn IFR, right? So here if you extend, you are going to get IFR. It is nothing but the field current corresponding to this point. Okay. So now we have this entire part is IF equivalent and this part is IFR. So then what is the remaining part? This is equal to the IFAR. So this is IFAR. Okay. So that is how this part is going to become the armature reaction in terms of the MMF.